Okay, where is my remote now? Okay, now guys, this is not actually new what we're going to be doing today, and we'll probably spend tomorrow on it as well. I just didn't teach you guys this stuff last year. It was Mrs. Race, so I just want to make sure that we have all our bases covered, and also we haven't done it in a while, and it is going to be in your test week test. So let's just do a nice summary of all of it and a couple of examples. All right, so given that f is a function.
This is, I mean,
Yep. And A is an element of the domain of F. I don't think you guys have seen that notation before. Guys, what is the domain? Domain is a set of all the x values. So basically they're telling you that A is an x value somewhere on this graph, all right, on this function. So we're going to discuss continuity and differentiability. We probably won't get to differentiability today. So firstly, just f of x is continuous at x equals a if, right, I'm not sure if you guys can actually remember this, but the f value, the function value at a, has to be equal to the limit as x tends to a from the negative side, so from the left of this function. We are going to do an example where we practice this as well. And that must then also be equal to the limit from the other side. So as x tends to a from the positive side or from the right of that function. All right, so guys, you're going to have to do 3 separate calculations and end up with the same value for all 3 of them. And then that will be, if it's the same value, then it will mean that it's continuous. Now, I just thought that we should quickly revise the types of discontinuities, all right? There's also a third one. I think you guys only discussed 2. Removable, you did the 3. Okay, good. All right, but let's just write them all down. So I'm going to do it in a different color. I hope you can read this. So types of discontinuities. Yeah, so that's what do you mean? Yeah, I'll put that first. So if these 2 limits are equal to each other, then the limit as x tends to a is also equal to that value, but you don't have to do it as a separate step, really. Okay, but is that what you're talking about? Yeah. Now, guys, if they're asking you, we are going to do it in the example. If they ask you, does the limit of this function at a specific x value exist? Then you would do just that one from the one side and from the other side. If they're equal, then that means that the limit exists. Okay, but you don't have to state that as a separate part, only if they're asking you. All right, so types of discontinuities. The first one would be a removable discontinuity. Now, guys, I'm just going to draw a little graph here as well. It's not to scale or anything, just to remind you of what it looks like. And remember, guys, this kind of went hand in hand with drawing split functions, right? I don't know if you remember that, but that was still a thing. So this is one option. If we draw it like that, and we say that that is our a value, Is that clear to everyone? Can you see what I'm writing there? Let me know. All right, so a removable discontinuity, it can either look like that, all right? So I'm just drawing a dotted line going down just to show that these two have the same A value, all right? But it's basically where a part of your graph has literally been removed. Okay, so on a graph, it's quite easy to notice that. It's not always easy to actually understand if it's just given in terms of like written stuff. So what's happening here, guys, is the limit from the left would be equal to the limit from the right. All right, so the limit here would exist, but the function value at that x value would not be equal to the limit. Does that make sense? Can we see that on the graph? All right, so the limit from the left would be equal to the limit from the right because they would tend to whatever this value is here, all right, this y value. But the actual function value, so f of a, would not be equal to that y value that you would have as your limit. Okay, so that is what's happening here. F of a would not be equal to the limit as x tends to a of f of x. Now notice, guys, that I'm not putting a plus and a minus, all right? Because we've already discussed that on this kind of graph, the limit from the negative side would be equal to this y value because it is tending towards that y value, right? And from the positive side, it's also equal to that y value, whatever it is, because it is tending towards it. And like I just said, if these two limits are equal from the negative and the positive side, then we say that the limit exists. Yes.
Does the solid point have to exist?
No. No, it doesn't have to exist. All right. So I'm actually going to write that down next. So this point, it could also just be left out. All right. They just, yeah, it does not even have to be a value for f of a. So we can add that in. So f of a does not necessarily have to exist. So guys, they can give you just this information, hey, without the graph. They can just give you this little bit and say, what does that mean? Is there discontinuity? What type of discontinuity is there? All right, so I'm hoping that this makes sense, that the actual function value is different from the limit value at that x value. All right, so that is what a removable discontinuity would look like, or if that dot just wasn't there at all. Okay, the next one is a jump discontinuity. I'm just going to write jump. All right. Obviously, it's types of discontinuities. So I'm just going to draw an example here. It could obviously look different. But yeah, it's just. Okay, so like I said, it doesn't have to look like this. This is just one example. But guys, obviously a jump discontinuity, it's quite clear that you are jumping from one y value to another. All right, that's why it's called a jump discontinuity. Now in this case, guys, do we agree that the limit from the left would be equal to 0 in this case? All right, but the limit from the right would not be equal to 0. Okay, so in this case, that limit doesn't actually exist at this x value, which is a. So for this to happen, the limit as x tends to a from the negative of this function is not equal to the limit as x tends to a from the positive side of this function. All right, then you get a jump discontinuity. They also could just say something along the lines of the limit does not exist at x equals a. And then you need to know that that means that there would be a jump discontinuity. Okay, are we fine so far? This is all revision, hey? It's all from last year's stuff. The third one is an infinite discontinuity. And that is like what you get at an asymptote, basically, right? Where your graph is tending towards infinity or negative infinity as it's going towards that value. So I'm just going to draw a little tan graph, basically, yeah. Okay, now this obviously doesn't have to be a tan graph, but I'm just gonna, that's the one that we are most familiar with in terms of having asymptotes. Right, and now that would be A in this case, and I'm just saying that that is F. Let me just label my axes here. Okay, so this happens that if we're looking at this graph specifically, as the graph is approaching A from the left, the Y value is tending to infinity, hey? So the limit here of f of x would be infinity, but obviously it could be drawn differently. It could just be done the other way around. Then it would be, yeah, the same thing happens if it tends to negative infinity, that you get that kind of discontinuity. And if we are looking at the limit as x tends to a from the positive side, so from the right, do we notice that our function value is tending to negative infinity? Okay, but in case of a different type of graph, it could be tending to positive infinity. Right, so guys, obviously in this case, the limit also does not exist, but it's more specific than with the jump discontinuity in the sense that it's not that it just doesn't exist, it's also that it's tending to infinity on the one side and negative infinity on the other side. All right, and there is a gap there. There is a discontinuity where you have your asymptote. So if you want, you can just write underneath infinite, you can write asymptote. All right, that is what that one is about. Yes, Sam? Oh, sorry. Thought your hand was up. Yeah.
I don't remember what well, I know what a hard one was. But what does it mean?
So can we discuss that when we're doing later examples, because it is going to come up.
Okay.
All right, but I just want to get through. Yeah, no, you are. We're going to do a lot of graph sketching still coming up. Okay, so we are going to discuss it still. All right, guys. I was going to write down stuff about differentiability now, but we only have like 10 minutes left. I want to do an example quickly. Yes? It depends on the question. All right, so sometimes, but again, we'll come back to these types of questions. All right, I know that last year you did you do questions where you had to specify which type of continuity or discontinuity it was? Yeah, so also when we start drawing them, you'll see we're going to do rational functions now. So we're going to have functions that I can just show you quickly in the book that are going to look different to what we're used to as well. So we're going to get stuff like, I think I did show you. Yeah, so we're going to even do like oblique asymptotes as well. So yeah, that stuff is still coming. So we're going to do a lot of discussion around asymptotes still. So don't stress about that yet. All right, I've written examples. It's actually just example, but anyway, whatever, it's happened. There we go. Number one, even though there's only one. Consider, and we are going to look at this split function, f of x, which is equal to this. And guys, you must also be able to draw this, right? We're not going to do it now, but first part would be a parabola, second part, dot, right, at y equals 4. Third part would be a straight line, all right? And it would go towards 1 and then 1, yeah. All right, A. Prove that the limit of f of x as x tends to 1 exists. Okay, so now they're not actually asking us whether this is continuous at x equals 1. They're just asking us to prove that the limit as x tends to 1 exists. Now, guys, for that, you're going to do limit from the left and limit from the right. And if they're equal, then it does exist. Okay, so let's do that. The limit as x tends to 1 from the negative side of f of x. Now, this second part that I'm going to write is optional, but it does often help if you just actually replace f of x with the specific function that we're looking at in that interval. So I'm just going to rewrite this as limit as x tends to 1 from the left. Now guys, from the left, are we looking at values that are smaller than 1 or that are bigger than 1? If we're coming from the left, smaller than 1. So what function would that be? Where is x smaller than 1? X squared plus 3. So this is what I'm saying. It's sometimes just useful to actually write that down. Obviously, if you don't have a lot of time, then you don't have to write it down, but it does help just to specify that it's that one. Okay, I'm just going to do this all in one line to try and save some space. Now, is there any complicated thing that I need to do with that limit? I can just sub 1 in straight. All right, so 1 squared plus 3 will just equal 4. Now we need to check what the limit of f of x as x tends to 1 from the right would be equal to. So limit as x tends to 1 from the positive side from the right. Again, this next part is optional, but it will obviously be 5 minus x, all right? Because if we're approaching 1 from the positive side, we're coming from where x is greater than 1. So it's 5 minus x. Again, there's nothing complicated there with that limit. We can just sub 1 in. So we're going to have 5 minus 1, which is 4. So the two limits are equal. Therefore, the limit does exist. All right. So therefore, now this is where it becomes a bit laborious. You actually do have to write this whole thing out. You have to say that the two limits are equal. Therefore, the limit as x tends to 1 of f of x exists. It does exist. And if they ask you for that value, what would it be? 4. Yes.
Would it change the purpose at all instead of like the 3 different to like just say x plus equal to x squared plus 3 x is less than 1, and then you just said x plus equal to 5 minus x is greater than and equal to 1. So then you won't have like the middle line.
Yeah, so then it would be the same thing in this case.
That it exists, you would just not have to you have to calculate at 4 and
so that only comes in if they're asking you about continuity, which is what we're going to do now. But then you would, if you've already done this, you don't have to do these two separate ones again. We can just use this one. We can just say that the limit is 4. And then because are you saying if this one was equal to 1 as well, it would also be 4. So you would then just say f at 1 is also 5 minus 1, which is also 4. Okay. All right, that's the first part. For B, now they're asking us, is f of x continuous at x equals 1? And then, of course, we can't just say yes or no with a smiley face. They do want us to justify your answer. Don't you guys feel like it's so short when you just say yes or no? Like there must be. You must say something else as well. All right, so justify your answer. Now, guys, continuity, it's those three things that must be equal. Now, in A, we've already proven that two of them are equal. All right? So all that we still need to do is that we need to prove that f at 1 is equal to the same value, which is 4. All right? And isn't it?
Yeah.
Right? If at 1, so when x is equal to 1, it is equal to 4. Right, and now instead of writing it as a separate line, I'm just going to do it all in one line. This is now equal to limit as x tends to 1 of f of x. Now, guys, because we proved already in the previous question that these are both equal to 4, all right, that means that the limit as x tends to 1, regardless of direction, would also be equal to 4. Okay, so does it make sense why we can write it like this instead of doing the two separate ones? If it confuses you, do the two separate ones, you'll get full marks. All right, so if you do x tends to 1 from the negative equals limit x tends to 1 plus, right, you would get the same marks. Therefore, f of x is continuous at x equals 1. Phew. Okay. You are going to have to do some homework for me, please. Exercise 16.1. We're on a different chapter now, guys. Finally, I feel like we've been doing chapter 15 for years. Exercise 16.1, page 178. And I want you just to do number 1. It is exactly what we did just now. All right. Also, does the limit exist? And then is it continuous? Okay. Yes. We're doing AP every day, guys, until test week, basically, unless I specify or unless we want to do some revision. And I must give you a note on remainder and factor theorem still, which I will print for you. Yes.
I'm writing everything just like that, most of the grading.
Mhm.
So I was wondering if you have any like suggestions or practice books that
Let me just quickly freeze here. I think Mrs. Court posted something about entity practice a while ago.
on there was so I started crying.
Really?